Welcome to Chapter 1, Section 4, where we're going to look at what is the definition of continuity and also talk about one-sided limits, which we've already sort of looked at a little bit, and then properties of continuity. And second day, we will work on the intermediate value theorem. So what does this mean? The limit as x approaches 3 of f of x is equal to -2. When I look at that, it's telling me the limit as I get close to 3 is going to end up at a height of -2. Does that imply that the function is continuous? Or do I possibly need to know more? Well, in my mind, I'm over here at 3. I'm coming into 3 from the left and the right, and the height is going to be at -2. So there's some function, however it's coming in and out of here, that approaches -2, or that the limit is -2. Does this imply that the function is continuous? So do I have an open circle here, or would this be filled in based on this information? Well, what I need to know is what is the value of f of 3, right? If I knew that, is f of 3 also equal to -2? Or maybe f of 3 is actually equal to 4, in which case this becomes an open circle for me, and then 3, 4 becomes a solid dot. And then it's not continuous, is it? So I need to know more than just what the limit value is in order to discuss whether a function is continuous at that point. So here we get into the definition of continuity at a point. F of x, the function is continuous at x equals c if, and c would be, some constant value. If 3 things happen, and you'll see I've got 3 pillars here that form the definition of continuity. So the function is continuous at c if all of these things hold. 1, the limit as x approaches c exists. 2, f of c exists, meaning I can get an answer. It's not just undefined, right? And then finally, pull it all together. Does the limit as x approaches c of f of x equal the same value as f evaluated at c? If that's the case, if all 3 of these things hold, and you can see how 3 really is the combination of setting these two equal to each other, if those 3 things exist, we know that the function is going to be continuous at c. And a function is continuous on an open interval if it is continuous at every point inside the open interval. A function that is continuous on the entire real number line is what we call continuous everywhere. And I'm not quite sure why that's like that, but what it says is -infinity to infinity. The words got jumbled there. Next up, looking at these graphs. The first graph, is this function continuous at c, and then explain it to me. Well, what I need to do, especially for AP, is explain, do these 3 conditions hold? If they do, I know I have a continuous function. So when I look at this first one, first thing that grabs my eye is this gap, right? We've got some jump going on here. And for that, I would have to say that f of x is not continuous at c because the limit as I go to c, as I approach c, does not exist. I do not approach the same value from the left as I do the right. So I could look at this, from both sides, from the positive side, and it does not equal the limit as x approaches c from the left side of c. So for that reason, I fail this condition. I can stop right there. I know this thing is not continuous. How about the next one? Well, when I look at this picture, would you not agree that statement number 1, the limit exists? The left side, it comes in at 2, it looks like, and the right side is coming in at 2 when I approach the value c. So Is that enough to state then that the function is continuous? Well, no, because I have to go on further now. Does f of c exist? Is there a point that is in existence as I plug in c? And for this one, we can clearly see that it is not. And therefore, if this fails, then we can say, or we have to say, that the function is not continuous at c, and there's the reason why. Picture number 3. Is this function continuous? Well, you know, one thing for continuity, and maybe you did this last year in pre-calc, if I just trace the curve, I cannot lift my pencil and then continue on. That would be, there's not a continuous flow there. So my gut feel says, no, it's not continuous. But why? And I have to be able to prove it. Well, the limit does exist. This would be true for this one. F of c is true. Now, is it true that 1 equals 2? Do these two match up? And in this case, we can clearly see that they do not. So we're going to conclude that the function is not continuous because the limit as x approaches c of f of x does not equal f of c. And I would be able to write f of c in this case equals 2, while the limit as x approaches c of the function f of x is clearly a height of 1, isn't it? And 2 does not equal 1, so this is not continuous. This last one, if I traced it with my marker here, never have to lift my pencil, do I? That's a pretty good indication that we've got a continuous function. Now, being able to support that would be 1, does the limit exist as I approach? We need a c in here. As I approach c, indeed it does. As I come in, looks like we're at a height of 2. So the limit exists, and the limit is equal to 2. C there. And it's equal to 2. Does f of c exist? Yes, f of c, well, if I look up here, it's also equal to 2. Therefore, the limit as x approaches c of f of c is equal to f of c. So this one is continuous, and for the reason that we stated, conditions 1, 2, and 3 all exist. And you have to be very explicit about this for AP to count your answer correct. You've got to state all 3 things. Example number 1, is this function continuous at 2? And if so, use the 3, or to conclude, we need to use the 3-part definition of continuity to perform our analysis. Well, what I'm looking at is a piecewise function, and I can see in this piecewise function that when x is not equal to 2, I use this rule, and when x is equal to 2, I use this rule. This basically is just naming a point. F of 2 is equal to 5, if I interpret that line correctly. And then over here, this means everywhere but at 2, everywhere x is not equal to 2. So all other points is going to follow, all other points are going to follow that rule. So where do we want to go from here? Well, let's use our 3-part definition. And I'm going to just clear my screen here for a moment. Number 1, I need to show that the limit as x approaches 2, because they want to know, is it continuous at 2? So I'm going to let it approach 2 of f of x. Well, it's going to approach 2. Here is what I'm concerned about, because I want the left and the right, and that will be taken up by this portion of the piecewise. If I tried to use substitution, I get 0 over 0. Therefore, our instinct says, let's try factoring this one. So x squared minus 4, x squared plus 4, all over x squared minus 4. I'm not going to factor the bottom because what I noticed is that I get a cancellation there. And now I can simply use substitution, and I have 2 squared plus the 4 gives me 8. Now, second part. Does the function have a value at f of 2? Does it exist? Well, yes, it does, because it's right there. f of 2 exists, and I know that f of 2 is really equal to 5. So my final thing that I need to conclude is, does the limit equal the value of the function evaluated at 2? So does the limit as x approach 2 of f of x equal f of 2? And of course we can conclude that no, it does not. It fails right there. Therefore, our conclusion that this is not continuous. There was the three-part definition that we have to follow, and it does not follow this one. We ended up with that being not true. So there you have it. So f of x is not continuous at x equals 2 because, and then you could restate this, and I'll just save some time. Example number 2, we got a three-part piecewise function here. Is it continuous at 1? Well, then I need to look at when c is 1, right? That's what I'm mostly concerned with. Okay, let's look at the limit. The limit as x approaches 1 of f of x, does it exist? I'm going to have to look at it from a left point of view and a right point of view. So let's go one from the right. That would be where x is bigger than 1. That's going to be 2 times 1 minus 1 equals 1. How about the limit from the left side? The limit as x approaches 1 from the left of this function. Now I'm going to be looking at this particular one where I square it. I'm going to have 1 squared, which also equals 1. Ooh, nice. Left equals right. Therefore, we can conclude the limit as x approaches 1 of this function is indeed 1. So we've got this one covered. We know what its value is. The limit is 1. Step number 2. What about f of 1? Does it exist? F of 1, well, it's defined right there, so indeed it does exist. It's equal to 1. Okay, step 3. Final step we need to consider, does the limit and the value at the point of 1 agree? And we can clearly see that they do. The limit as x approaches 1 of f of x is indeed equal to f of 1 because this was equal to 1 and this was equal to 1. Therefore, our conclusion is this function is continuous at x equals 1. So I've written in black my conclusion, f of x is continuous at x equal 1 because the limit as I approach 1 of f of x is equal to f of 1, as shown by my work over on the left, and I just didn't want to have to repeat those 3 conditions, so I just said, no, it's over on the left. Types of discontinuity, non-removable types. Let's cover those first. The first one, well, you can see clearly that it looks like we kind of have an asymptotic situation here, vertical asymptote, and we have, as we approach this value, let's call this value c here, we're headed to negative infinity here, and as I approach c from the right side, I'm headed to positive infinity. And since they're headed in opposite directions, this is an infinite discontinuity. And you could go through your 3 scenarios. The limit as x approaches c of f of x does not exist. Also, we can conclude that part 2 of that definition, f of c doesn't exist, therefore the limit does not equal f of c either. So many reasons why it's discontinuous. Number 2 here, the limit, I can see that I've got this jump discontinuity. Whoops, I think I might have given it away. Jump discontinuity. There is a gap between the left side of the limit as well as the right side of the limit. Jump discontinuity. How about removable discontinuities? Now, removable discontinuity, a removable discontinuity is defined as a continuity at c that can be made continuous if I find the appropriate value for f of c. So like if I could fill in the little gap or the little point, then it's called removable, like I could remove that discontinuity. And one type of that is the whole discontinuity. And right here we can see we have this linear function, we have this open circle. So it's discontinuous. However, I would be able to fill it if I could fill it in, if I could define that point, then I would have a continuous function. So these are called removable discontinuities because it's quite easy to fix the scenario. And the next one, the next example that we have is also whole discontinuity. We have the whole, but we also have this one defined there. If I could have defined this maybe a little bit differently, this looks like a height of -1. If I had just changed this to -1, I would have a continuous function when x is at -2. And so therefore it's called a removable discontinuity. Still discontinuous, but it's removable. Example number 3. Is this function continuous at x equals 2? If it does happen to be discontinuous, is it a removable discontinuity? Okay, well, let's take the approach. If we want to know about continuity, we've got to discuss 3 things. The limit as x approaches c, and the c value that we're looking at is 2. So we're interested what's happening around 2 of this function, not f of x, but g of x. Well, can I plug in 2 into this? Well, it looks like I probably get 0 over 0 on this one. And therefore, let's try factoring. So the limit as x approaches 2, if I factor the top, this will be my factoring. Check it out, it will work. And then we get the bottom factor, that's a problem, to cancel away. Now I can plug in 2. I get 5 times 2 minus 1 gives us a value of 9. Let's go on to the second part of our continuity quest. So f of 2, does f of 2 exist? And unfortunately, 2 is not in the domain. The domain would be all reals, except that we cannot have x equaling 2, right? So this is an undefined point when x is 2. And then 3, obviously, this would be my conclusion that since f of 2 doesn't exist, it is discontinuous. We could stop right there, couldn't we? So g of x is discontinuous. And we got to discuss where is it discontinuous? Discontinuous at x equals 2, really by a whole discontinuity, which is removable. Whole discontinuities are removable discontinuities. Okay. And then there's a picture of what is going on for us here. We do have that whole discontinuity, but otherwise it's pretty much a linear function of 5x minus 1. Okay, what you're looking at here is the definition of continuity on a closed interval. So what happens if I'm looking for continuity on this closed interval from A to B? Picture A here has a good description. Notice we've got from A to B with the brackets, so the endpoints are included. Well, unfortunately, I can't see to the left and the right of B, so by other means, it's like, well, the left has to equal the right in order for the limit to exist. When we're looking at continuity on this, these rules take over. And notice how we're coming into A from the right side. So the limit as we come into A from the right side, does that limit equal the actual f of A point? And in this case, it does. And then from B, since B is to the right, I want to come into B from the left side of it. So as I'm coming into B from the left side, does the limit's value equal the point's value? Do they map out together. And in this case, they do. So we do say that this function is continuous on the closed interval, even though I really can't see what's going on to the left or right of the function. It's just, you know, follow this one-sided limit type idea and you'll be able to answer it. Part B here, I could talk about, well, I've got open endpoints, so I would say this one is continuous from A to C, and then we have continuity from C to B over here. But they would have to be open intervals. I could not discuss closed intervals because my functions aren't defined on those endpoints. And I think that's good enough. 20 minutes is a long video, and I'll see you in class tomorrow.